Today I want to talk about artificial intelligence. In fact, I'm going to make several videos because artificial intelligence touches pretty much every aspect of education as we see it today. But before I begin, really, I want to have a look at what artificial intelligence is, rather than look at its applications. I'll look at its applications later in another video. And let me start by saying I've been working for some time with a friend and colleague, Professor Lee at Beijing Normal University, on questions related to artificial intelligence. And ultimately, artificial intelligence is about making decisions, and we've found useful a distinction made by Donald Broadbent. Donald Broadbent was a British psychologist, member of the British Psychological Society, who honoured him in the 1990s by naming a series of lectures after him, Broadbent Lectures, and in the first Broadbent lecture, Donald Broadbent himself set out, as he saw it, the future of decision making, not only for psychology but in terms of information processing as well. And he distinguished between symbolic reasoning and sub-symbolic reasoning. Symbolic reasoning is where you have a clear model of what's happening, of how the system that you're looking at operates. You have a comprehensive overview and you design your approach. Whereas sub-symbolic is you look for small changes, incremental improvements in order to get towards the answer that you want. The illustration he gave was of designing a fire escape system, a system to be used in cases of fire. You want somebody to come in and design the system, somebody who knows what they're doing, who knows where to put the buttons that you press to sound the fire alarm. You need to place the sirens and klaxons and bells in the right places. You need signposts up that show you where the escape routes are. All of those things, you need somebody, a central intelligence designing the system. And one person or a small group of people can do that because they can have a clear model of what's going on in a building in the event of fire. But that won't solve all of the problems. You also need decision making distributed among a lot of people. You need everybody to know what to do if they see smoke or flames. You need everybody to know what to do if they hear the fire alarm. You need everybody to know where the nearest route out of the building is and where they have to assemble when they've got clear of the route, got clear of the building, so that you can count them and make sure that everybody's safe. That information, everybody needs enough to act, but they don't need to design anything. They just need to, if they've come across a corridor that is blocked by smoke, they need to know how to seek another route out of the building. So Broadbent distinguished between systems that need to be designed by a single intelligence manipulating a model of the system, and decisions that need to be made, information that needs to be distributed and can be made by a network of people. And what I'm going to look at today is neural networks. Now, neural networks are not the only form that artificial intelligence can take, but in terms of the large language models that have become so prevalent and so important recently, neural networks are an important part of those artificial intelligence machines. And what I'm going to do, I'm going to look at a website. It's run by an organisation called TensorFlow.org, and it's their playground for neural networks. And you can, after watching this video, you can go onto the website and you can play with it for yourself. But this is what it does, and this is how it explains what a neural network does in artificial intelligence. Now, a neural network, don't be fooled by the name it's got. It's got actually very little to do with the brain, although it may have been inspired by how we think the brain works, and it's got nothing to do with how the brain works, except perhaps we might like to think about a brain and imagine it in terms of neural networks, but the terminology is definitely brain-like. A neural network has a number of neurons, and the neurons are divided up so that there's an input layer and there's an output layer, and in between there are a number of hidden layers. And I'll talk about how many hidden layers there might be. But in the playground, TensorFlow's playground, we're going to give it a pattern of dots, blue dots or orange dots, and we're going to ask we're going to tell the neural network the position of a dot, its x and its y coordinates, and we're going to ask it to guess whether that dot will be blue or orange, and it will divide the space up as it learns what colours go where. As it learns which colours go where, it will divide this space up into orange and blue to show its best guess. And it feeds the information into the next layer of the neural network. And each of those then pass on the message to the next layer. And eventually to the output layers. And we'll feed a pattern into the neural network, and it will iteratively try to guess which dots will be blue, which dots will be orange, and on each guess it will then be given information about how accurate it is, and it will adjust the weightings, which of the neurons are given more weight in deciding the outcome. And progressively, you can see this is distributed knowledge. It's not one person or one thing having an overall decision of the view of the picture. And you'll see as the neural network learns which pathways are being emphasized, which pathways are being built up. The thicker will be shown by thicker lines, and you'll be able to see what each of the neurons, which pattern each of the neurons is looking at, and how they add up towards the overall conclusion. And if we put in a very simple pattern, a fairly simple neural network will resolve it. It will, even with one or only two internal hidden layers, it will be able to tell you that the pattern will quite accurately predict. But as the patterns get more and more complex, the difficulty with which the pattern is resolved it'll take longer and longer, more and more iterations for the network to resolve and to get to a satisfactory solution. And Then we might also look at, well, it depends what you call a complex pattern. In the examples you'll see, I'll show you now running through the neural network, looking at it in order to resolve the patterns into predictions as to whether dots are orange or blue. What we're going to start with is a simple pattern. Blue dots to the upper right, orange dots to the lower left, and you can see that with just a single input layer, measuring the x and y coordinates of the dots, it fairly quickly resolves it into a clear pattern. The blue areas where it expects to find blue dots, the orange areas where it expects to find orange dots. If we give it a more difficult pattern though, if we give it a checkerboard pattern, it's not going to be able to resolve that so easily. It's vaguely thinking that the upper right is blue. It's got large areas where it's expecting to find orange dots, but the patterns are not clear. So what we're going to do is we're going to add in a hidden layer, and now it does better because it's got more options. You can see that the neurons in the hidden layer are looking at diagonal patterns, and when they're overlain one on top of the other, it can produce a composite pattern that is more accurate than before. And the more neurons we add in to the more hidden layers, the clearer it becomes in resolving the dots into a pattern that is intelligible, making predictions about whether blue dots and the orange dots are likely to be on that square that we provided. Now, we can add more and more hidden layers in and more neurons in each hidden layer, and that should make it much better at resolving the slightly more complicated patterns. Here you can see with 4, 5 hidden layers, 8 neurons in each layer, it fairly quickly resolves the checkerboard pattern into something that we would recognize. The line above the output, the top right side, that line shows you how the neural network is becoming more confident, how it's settling, and how it's accepting that it's got the right answer. Here's a more difficult solution still. 2 concentric circles, an orange circle around the outside, blue circle in the middle, and again it's taking time to settle, but it is fairly clear that it is resolving this pattern, and it is able to decide where it expects to find blue dots and where it expects to find orange dots. If we run it again it will resolve it quite quickly. Look at the line at the top right that it's settling down to, saying that it's found the answer that it's content with. But notice when you try this for yourself that the weightings of the different connections between different neurons will not be the same every time. It will resolve the problem, it will resolve the pattern into predictions, but it will not produce the same result every time. Now this time we're going to try a much more complicated pattern on it. Actually, this is a pattern that you and I would think of as simple. It's as 2 spirals. It's a blue spiral and an orange spiral together, rolled together as though perhaps like rolling 2 sheets of paper together. But it's a pattern that's very difficult for the neural network to creep up on iteratively, bit by bit, approaching it. And you can see that there are still quite large areas of the pattern that are white or only palely shaded blue or orange, and that juddering is an indication that it's not able to get over some sort of hump in the difficulty, hump in finding out where the blue dots and orange dots are expected to be. The line above on the top right that's showing you whether it's settled or not all that shuddering and juddering is it going backwards and forwards, jumping from one solution to another. It will eventually resolve itself into something that looks more like a pattern. But remember, this is a pattern that you and I, with our human eye and our view of what it is to design a pattern, thinking symbolically, thinking of it as two spirals, we can resolve this quickly and without any difficulty at all. Thinking symbolically, this particular pattern presents no great problem. But thinking subsymbolically, the neural network is having really quite a lot of difficulty deciding which areas to colour in orange and which blue. It's settled on something now, but even you and I, as we look at it, can see that it's making some rather odd predictions about spaces where there are not actually dots. So that simply is how the neural networks are functioning. It's good, the networks are good at the problems that can be approached piecemeal, creeping up on them by successive iterations. They're not so good at decisions and handling information where you need an overall pattern of the decision to be made, where you need an understanding, a holistic view of the problem that you're trying to solve. Those things will need a different kind of artificial intelligence, and of course telling the difference between the subsymbolic, which these networks are excellent at solving, and the symbolic, which need a more coherent, holistic design view, deciding which approach is necessary. Broadbent himself was optimistic that neural networks would eventually be able to handle both types of decision, the symbolic and the subsymbolic. I think that's not necessarily true. You can see that the individual neurons don't have an overall view of what the pattern is that they're trying to resolve. They have a partial view, and each neuron doesn't make a decision about how to pass the information forward. That's in the hands of the overall network. And what I think that means is that these systems are very good at subsymbolic reasoning and not so good at symbolic reasoning. And by analogy, you can see a similar pattern in social media, where each person passes on the tweet or the message or whatever it is that they've received from somewhere else. And if it looks interesting, they pass it on, but they don't necessarily think about whether it's true or not. This is funny. If it was true, it would be interesting and important. Just in case, I'll pass it on. And because the criterion for passing information forward through the network, through a social media network in that case, is not whether it's true or not, then fake news gets spread as quickly or as perhaps even quicker than the truth, because it's more interesting. Something that's out of the ordinary, unexpected, and therefore probably untrue, gets spread further and faster than something that's mundane, fully to expected, and therefore quite likely to be true. So these networks are really good at some particular kinds of problems, but solving some particular kinds of problems, but not at every kind of problem that you might be faced with.